Please let me remember you that after the talk we will have the group picture. Okay. Now, with the second talk of the afternoon, it's a pleasure to present Ethan Cotterill from UNICAMP, Campinas, who's going to talk about, is the same? No. Tropical semirings and curved singularities. Thank you.
So it's a pleasure to be invited to speak in this conference in honor of Fernando. Fernando is my mathematical older brother, and I also had the pleasure of knowing several of Fernando's students, and I also wrote a paper with one of his former master's students. So it sort of means a lot to me personally to be able to speak at this conference. So I'm going to talk about something I think in some sense that's a little bit more closely aligned with the mathematics that Fernando was exploring at the beginning of his mathematical career. What I'm going to say is quite combinatorial, so so I hope you'll be indulgent. So what we're going to talk about is the following. It's going to be work with a bunch of different people. To motivate what I'm going to talk about. So as you guys all know, it's often interesting when studying an algebraic variety to study the space of morphisms from P1 to that variety. And when the target variety is Pn, somehow the space of morphisms of fixed degree is not particularly interesting because given that every morphism is spelled out by a vector space of homogeneous polynomials of degree d, essentially the space of morphisms you can think of as an open subset of a Grassmannian. But things will become a little bit more interesting if instead of simply fixing the target dimension and the degree of morphisms from P1 to Pn, we also fix the arithmetic genus of the image. So MNDG is going to be a parameter space of maps with images of arithmetic genus G of degree D from P1 to Pn. And I'm going to call this, I want to think of this as a generalization of a Severi variety. The Severi variety being corresponding essentially to the case when the target dimension is 2. So the most basic question you might ask about one of these parameter spaces and about its topology is whether or not it's irreducible. And when n is 2, the answer is always yes. And in particular, what we know from Joe Harris's work on the Severi problem in the 1980s is that the space of morphisms of degree D and arithmetic genus G is going to be the closure of the space of morphisms whose images have exactly G simple double points or nodes. So by double point, I think you know what I mean, but something like this. So there would be G of these. So the situation is quite nice when we look at planar images. But as soon as the ambient dimension is at least 3, in general, these parameter spaces will not be irreducible. And I'll try to give you some good reasons as to why that is the case. And everything that I'm going to say is somehow going to be very crude, and it's going to be predicated on dimension estimates. In particular, what we're going to do is inside the space of morphisms, inside of MNDG, we're going to focus on maps whose images have one bad singularity, a value semigroup. So they have one bad singularity of arithmetic genus or delta invariant G. And I'm going to actually specify the value semigroup of the singularity. So I'll explain what that means in a couple of minutes. In fact, I'll explain right now what that means, I guess. So in the simplest case, we have a unibranch singularity. So in other words, instead of looking at this sort of local situation, I have a cusp. And the point is that we can parameterize the cusp locally by power series. And the local power series incarnation of the singularity is just dual to a map of rings, where the target ring is a power series ring in T. And what's nice is that C double brackets T is equipped with a non-Archimedean valuation that simply computes the order of vanishing in T equals 0. And then what I'm calling the value semigroup is going to be the composition, is going to be the image of the ring map composed with the valuation. And very loosely, you can think of this operation of computing the value semigroup as sort of computing the logarithm of the local algebra of the singularity. In the more general situation where we now have an arbitrary number R of branches, well, in that case, I have to parameterize each branch individually by a power series. And the dual picture of that parameterization is a map of rings where now the target is just a product of power series rings. And again, the value semigroup is the composition of the ring map with the valuation, where now we just take the product of the Ti-adic valuations on each of the power series rings. And the underwriting philosophy here is that the topology of this parameter space, whatever it is, should be controlled by the arithmetic properties or the combinatorial properties of the value semigroup. Okay, so if there's anything that's not clear, please feel free to stop me. So I said that I wanted to produce reducible parameter spaces via dimension counting. So to explain how that's going to work, the first thing that I want to do is give a dimension counting heuristic. So in producing conditions, algebraic conditions on maps, what I mean is producing algebraic conditions obviously on the coefficients of these parametrizing morphisms. And the baseline heuristic that you should have in mind should be the dimension count for the G-nodal locus. So what's easy to see is that the G-nodal sublocus of M and dg has codimension n minus 2 times g inside of the space of all morphisms of degree d from P1 to Pn. And the reason for that is actually very simple. It's a linear algebra count. So the idea is that if you look at a simple double point and you fix the target and the two preimages, then that imposes exactly 2n linear conditions on coefficients of maps. And then when you vary the target, you subtract n conditions, and then you subtract 2 extra conditions coming from the variation of the preimages. So that simple double point selects for n minus 2 algebraic conditions. And then you have to check, but it's not hard to check, that these conditions are in fact additive across the nodes. So that explains the codimension of the G-nodal locus. So in particular, the point is that if it were somehow the case that M and dg were irreducible, then its codimension inside of M and D would have to be at least n minus 2 times g. Because in particular, M and dg would have to be contained in the closure of the G-nodal locus. But that turns out not to be true. So in effect, I'm going to explain to you why that's not true in general. And at this point, there's kind of a natural dichotomy. So there's dimension counting for cusps, and then there's dimension counting for multi-branch singularities. So I actually want to focus quite a bit on cusps, but then say something interesting, hopefully, about the multi-branch case at the end. And say something specifically about the underpinning combinatorial objects that account for these dimensions. So let's say we want to account conditions imposed on morphisms by cusps with a given value semigroup. In counting conditions, it's useful to distinguish between two types of conditions. So there are conditions that I'll refer to as ramification conditions or inflection conditions, which just describe sort of how locally twisted in space the image of your morphism is. And those conditions are just selected for by vanishing of derivatives, specifically ramification conditions. So if we pick out vanishing orders of sections in the preimage of the cusp, let's say that those vanishing orders are A0 to AN, then what I'm referring to as ramification is just the cumulative deviation of those vanishing orders from the generic sequence of vanishing orders. And we can refine that a little bit and refer to ramification type as just being, instead of computing the sum of those differences, we can actually record the n+1 tuple of differences. Actually, for me, A0 is always going to be 0, so it's a bit of a red herring, but that doesn't matter too much. So I'll call ramification type the vector that records the difference with respect to the generic sequence. And then what we can do is we can refine the parameter space associated with morphisms whose images have a singularity of given value semigroup. We can further refine that parameter space according to ramification. And if we do that, we essentially get a generalization of a Schubert variety inside of a Grassmann. OK, but those are the simple conditions. And the more subtle conditions are what, for lack of a better word, I'll just refer to as beyond ramification. And those extra conditions, those more subtle conditions, arise from specific arithmetic or additive properties of the semigroup. Or in other words, they come from the multiplicative structure of the local algebra of the cusp. So ramification conditions are easy to understand. Conditions beyond ramification are a bit harder. And I want to give some kind of combinatorial model that at least conjecturally accounts for these extra conditions beyond ramification. In order to present the combinatorial model, I need to tell you a little bit more about the combinatorics of value semigroups attached to cusps. So when your singularity is a cusp, the semigroup, so it's a sub-semigroup with the natural numbers, and it's a numerical semigroup, which just means that its complement is finite. And the number of elements in that finite complement is exactly the contribution of the singularity to the arithmetic genus, or in other words, the delta invariant. So in our particular situation, we're going to be focusing on instances in which the number of elements in the complement, it is exactly the arithmetic genus of our curve. OK, well now, another basic fact is that if you're given a numerical semigroup of genus G, it's always determined by its truncation in its restriction to natural numbers between 1 and 2 times G. And that's exactly because G is the number of elements in the complement, if you think about it.
You don't have any Gorenstein partition?
No, because Gorenstein just means, Gorenstein would ensure that the conductor is exactly 2 times G. But in general, it could be less than or equal to 2 times G. So it doesn't matter either way. OK, so given that the semigroup is determined by its truncation to the numbers between 1 and 2G, we're going to now use the following recipe. We just decree that, so I'm going to each numerical semigroup, I'm going to assign a lattice path inside of N2. in which if I imagine for each traversing the numbers between 1 and 2g, every time I encounter an integer that belongs to the semigroup, I go to the right by 1 unit, and every time I encounter a number that belongs to the complement, I go up by a single unit. And in that way, I'll end up with a lattice path of length 2g that starts at the origin and ends in the point g comma g. And the idea is that if I represent my semigroup this way, then conditions on morphisms associated with singularities of that given semigroup, conditions arising from ramification will show up as boxes, so in this grid below the path, and conditions beyond ramification will show up as boxes above the path. And I'll give a picture of this in a second. Yeah, this is exactly what I just said. Yeah, so in fact, I'll give a picture that corresponds to this example where the semigroup is minimally generated by numbers 2 and 15. So you can check that this is a particularly nice type. It's hyperelliptic. It's called that for historical reasons. Actually, it just means that 2 belongs. Combinatorially, it just means that 2 belongs to the semigroup. And if we assume that n is 4, g is 7, and d is much larger than g, let's see what happens in the next slide. Yeah, so if we now look at the corresponding parameter space of morphisms, the idea is that, yeah, I think there are actually typos in my, sometimes I write mnd comma s, some other times I write mndg comma s. It should probably be mndg comma s. They're supposed to mean the same thing. This parameter space will contain maps with various possible ramification profiles in the preimage of the cusp. And a generic possibility would be that the vanishing orders, that the non-zero vanishing orders in the preimage of the cusp be 2, 4, 6, and 8. Why do I say that's the generic possibility? Because they're automatically positive integers that have to belong to the semigroup. So they have to be, in practice, they have to be even numbers. So I've just picked the minimal ones. And now in our combinatorial representation of the semigroup, so the semigroup is this staircase, this diagonal staircase, and I've marked these horizontal segments in the first 4 rows according to the corresponding elements in the semigroup. And now what I claim is that you should think of the gray boxes underneath the path as being selected for by ramification. And you should think of the red-colored boxes as being selected for by conditions beyond ramification. And the reason for that, roughly speaking, is as follows. So first of all, my target dimension is 4. So the idea is that each one of these columns corresponds to a parameter. So if the parameterization locally is by functions f1, f2, f3, and f4, then fi corresponds to column I. And then the reason that the ramification conditions are in gray is that for each of the boxes underneath the path corresponding to the semigroup, I've just marked off exactly as many derivatives as need to vanish in order to be consistent with the vanishing orders. So that explains the ramification conditions. What explains the conditions beyond ramification? Actually, there's a mistake here. So the arrow should actually point, this arrow should actually point here as opposed to here. That was just an orthographical mistake. So I want to explain briefly the conditions beyond ramification. The idea is as follows. If you look at this segment marked by 4, the red box directly above it is going to correspond to the following condition. So if you imagine computing f1 squared minus f2, because I've just assumed, sort of normalizing things, that f1 and f2 have leading coefficient 1, well, f1 squared minus f2, their leading terms cancel. And so generically, what you would expect is that the valuation of their difference, the valuation of f1 squared minus f2, just be exactly 1 more than the valuation of f1 squared. That would be the generic situation. But the point is that's prohibited because of our choice of semigroup. So that imposes an algebraic condition, which is exactly the condition in this first red box in that second column. And then there's some kind of inductive prescription that allows you to produce conditions associated with the boxes above it in the same column. And then in general, if you move from column 2 to 3, instead of looking at f1 squared minus f2, this one would be f1 cubed minus f3. This one would be f1 to the 4 minus f4, which is what I explained down here. And then there's some inductive scheme that allows you to deduce the conditions in the boxes above in each column.
So each box corresponds to a dimensional condition?
Yeah, the idea is that each of these conditions would be additive. They're just algebraic. They're all mutually independent algebraic condition. OK, so that's what I just said. Yeah, so if you look at this picture again, oops. What you notice is that the total number of boxes minus 1 is exactly the area of this rectangle sort of in the middle of the diagram, n minus 1 times g. And that turns out to be a typical situation. So what we proved is that in general, I think actually we have to modify this degree assumption slightly, but in general, in the hyperelliptic situation, modulo d being sufficiently large relative to g and n, that the codimension of this hyperelliptic locus inside MNDG, sorry, inside of MND is exactly n minus 1 times g. And we also conjecture, sort of going beyond that, that each of these spaces, MND, G, S, or S0, where S0 is a hyperelliptic semigroup, is paved by subloci that are irreducible and unirational that we get by fixing the ramification profile. That's just a conjecture. I mean, that conjecture would be sort of automatic if we could prove that our combinatorial model for algebraic conditions were valid in general. OK, and then I want to say a few things about the more general situation. Dimension counting for, this should read MNDG, S, when the underlying singularity is a cusp. I just want to give some kind of feel for what the ingredients going into dimension count will be. So we're going to focus on, we're going to fix ramification profile K. I'm also going to fix a presentation for my semigroup in terms of minimal generators. And then one important ingredient in dimension counting in general will be this arithmetic function that to a given element, that for example, to a given element in the semigroup associates the number of elements in the complement that are strictly greater than it. Another key player in dimension counting in general are what are known as Betti elements. And the reason why these are important is that they are sort of the elements that control the additive structure of the semigroup. I give a formal definition. I don't want to harp on this too much. Betti elements are exactly those elements that have qualitatively distinct factorizations in which qualitatively distinct is a technical condition that's defined over here. So if I single out a given element of my semigroup, and I look at all of its factorizations in terms of, so actually, the factorizations that I will be interested in, yeah, I think there's, for us, factorizations really need to be in terms of minimal generators of the semigroup together with elements of the ramification profile. And then the idea is that we can divide the space, we can stratify the space of factorizations of a given element into equivalence classes by decreeing that two factorizations are equivalent if we can relate them, if we can relate their coefficient vectors, the coefficient vectors associated with factorizations, by a chain in which, so all of these coefficient vectors correspond to valid factorizations. And the idea is that between any two vectors in the chain, we require the usual dot product to be non-zero. And a Betti element is going to be an element for which there are at least two equivalence classes of factorizations. So for example, yeah, so I tried to give an example of Betti elements. So if we fix a choice of semigroup 410, the semigroup generated by 410 and 15, and we fix this particular ramification profile, what I claim is that the set of Bellian elements is 8, 12, and 20. And sort of the reason, I mean, this isn't a rigorous check against all of those definitions, but the idea is as follows. We need to compute the set of Bellian elements with respect to, yeah, actually, so what this should actually read, what this means is Betti elements with respect to, so these are factorizations in terms of 4, 8, 10, 12, and 15. And then the idea is that I've just exhibited for each of 8, 12, and 20 factorizations that turned out to be qualitatively distinct. Okay, so the idea is that in general, to calculate dimensions, we single out the set of Betti elements attached to our semigroup and ramification profile. And then for each Betti element, we form a set of representatives for equivalence classes of factorizations. And then the key player turns out to be a matroid. So I wrote the vector matroid on these differences. The idea is that for each, Betti element, I just have to single out a single reference vector, which is then fixed, and I subtract each of the other coefficient vectors against it. In general, so a matroid is going to be an abstract, some kind of abstract generalization of a vector space. I don't want to give the definition, the actual definition right now. One way, actually, I will give a definition. I won't give the standard definition. One way to specify a matroid is by specifying the underlying finite set, the ground set, together with the set of minimal dependent subsets, or in other words, the circuits of the matroid. And the characteristic property of circuits is that they satisfy this circuit elimination axiom. And what's interesting is that it turns out to be the circuits of this vector matroid that, at the end of the day, at least conjecturally control the dimensions of these parameter spaces. So, yeah, I don't want to get lost in all of these definitions, but the idea, so at the end of the day, a conjecture that says that the codimension of the space of maps with given value semigroup and ramification, given numerical value semigroup and ramification profile, is given by, so there's a contribution from ramification, which is the sum of the ki's minus i's minus 1, together with, there's this part in the middle in which we sum over Betty elements. So the idea is that if you think back to the picture that I gave of the hyperelliptic case, the Betty elements in this instance are exactly those elements. In this case, they're exactly 4, 6, and 8. They're exactly, in general, the Betty elements exactly index those columns in which conditions beyond ramification appear. So in the general situation, I hope I defined everything here. I'm worried that I missed a definition. But in this middle piece, we have a sum over Betty elements. So this is a first approximation to conditions beyond ramification, in which psi of s is just the number of equivalence classes of factorizations. And then the idea is that there are these corrections. So we're multiplying for each Betty element. There's the number of equivalence classes of factorizations times this row of s, which just computes the height of the column above the segment in the lattice path. But then there are these corrections, and these corrections ultimately are controlled in some relatively complicated way by the circuits of this vector matroid. So we have a conjectural picture of dimension counting in the cuspidal case. I also wanted to mention that we were able to produce some interesting new families of reducible severity varieties by considering, what I'll refer to as generic cusps. So this would be a situation where there are actually no conditions beyond ramification. So this goes in a direction that's sort of orthogonal to the combinatorial model that I was just giving, because in this situation we don't have to account for conditions beyond ramification at all. But the idea is that in order to produce the dimension estimates that we need, we actually need estimates on the genus of a generic cusp. So in other words, if you fix a particular ramification profile and you just require that all higher order coefficients of parametrizing functions are generic, you want some expectation for what the corresponding value semigroup is. So we're able to control, in some sense, give estimates for how large the genus of the corresponding value semigroup will be. Okay, so in the time that remains, I wanted to say something about dimension counting for multiple points. For multi-branch singularities. And in particular, I'm going to focus on the case of multiple points, which are sort of, in some sense, opposite to cusps. So concretely, we'll consider R-fold multiple points of some embedding dimension L. And the idea is that in this situation, counting conditions imposed by multiple points is actually easy because it's easy to count the number of conditions imposed by incidence. That'll just be r minus 1 times n minus r. And then there are additional determinantal conditions. It's sort of well known that there are n minus l times, that the condition for being embedding dimension L is codimension n minus L times r minus L. So the real issue in this instance is controlling the structure of the value semigroup associated with a multiple point. And in general, this isn't going to be easy. I mean, first of all, the value semigroup of a multiple point, it's a subsemigroup of n to the r. And for example, as soon as r is strictly greater than 2, you can't even visualize these things in any reasonable way. There is one very easy case, though, which is the situation in which the embedding dimension is 2, and the multiple point is locally planar. And the reason why it's easy to compute the genus in this case is that, so if you imagine having a planar multiple point, well, you can just deform, I mean, this isn't really an argument, but morally you can just deform these lines so that they become a generic arrangement. So there are 4 of these. And in general, so in general, what you would expect anyway is that the genus of a planar multiple point is just given by this binomial coefficient r choose 2. And we can prove that explicitly, sort of computing the value semigroup. But if the genus is r choose 2, then and we sum the number of conditions imposed by, so incidence, r minus 2 times n minus 2, together with, that's incidence, which is r minus 1 times n minus r, together with embedding dimension, which is r minus 2 times n minus 2, then as soon as r is sufficiently large, that number of conditions is strictly smaller than n minus 2 times the arithmetic genus, which implies that that these severity varieties in general are excess dimensional as well. Okay, so then we can ask for results about multiple points that aren't necessarily locally planar, and we don't have we have pretty sketchy results in this situation, but I wanted to give some ideas that I think give a new point of view on how you should think about these value semigroups anyway. So the first idea, which sounds simple but somehow completely changes the game, is that instead of looking at S, instead of viewing S as a subset of n to the r, we should simply add infinities to each copy of n and look inside of sort of this compactified version involving infinities. That sounds pretty stupid, but turns out to be a useful idea because, well, so the idea is that as soon as you add infinities, it turns out that the fundamental object in this game is the support of the parametrizing functions of the singularity. So in other words, if I record exactly those monomials in my product of power series rings that appear in the parameterization of my singularity, in instances where the coefficient attached to a monomial is non-zero, I say that that monomial, or collection of monomials, belongs to the support. And these infinities, these instances of infinity, just correspond to cases where the coefficient of the monomial is 0. So it turns out that you can, it turns out that the value semigroup of the singularity, now viewed inside of, so I'm calling the value semigroup S inside of n bar to the R. That value semigroup is additively generated by elements of minimal support, by which I mean maximal numbers of infinities. And essentially the reason for that is that it's the homomorphic image of what I'll call the tropical support semiring of the singularity, which is a generalization of a matroid, and which records exactly the supports of the parametrizing functions of the singularity. And I'll try to maybe be a little bit more explicit about this in a second. And then the point is that at least when we restrict ourselves to looking at multiple points, we can understand, we can compute these value semirings, and even these tropical support semirings explicitly. Yeah, maybe, well, yeah, modulo some genericity hypotheses. Okay, so for example, we proved with Christian Garay, we proved the following statement. If X is what we're calling a very uniform essential line arrangement, essential just means that the lines all pass through the same point. Uniform is a strengthened version of uniformity in the sense of a uniform matroid. It's actually defined, it's very uniform means uniform with respect to sort of an infinite set of interpolation problems that I'm not going to have time to get into right now. But it's sort of a very strong version of uniformity. So if we impose that there be R of these lines, and that the embedding dimension be n, then we give at least it's an explicit recipe, an explicit recipe for calculating the associated value semigroup. This conductor element is sort of the element beyond which, so if you increase any of the entries, if you go above D in any given direction, then you remain inside the semigroup. So the idea is that this recipe specifies explicitly exactly which elements of the semigroup, exactly which elements strictly less than this DDDD vector belong to the semigroup. However, it's arithmetically complex enough that, in fact, the only case in which we can sort of write this down in a completely transparent way is when n is equal to 2. Yeah, so maybe the very last thing that I'll say is I wanted to try to make explicit a little bit more the second idea about the tropical support semiring, so what I'm actually talking about. So we give a generalization of what in the matroid literature are referred to as cycles. So one way to specify, so I mentioned before that one way to specify a matroid is according to its circuits. Circuits are always minimal dependent subsets, and cycles, by definition, are unions of circuits. And cycles satisfy essentially the same elimination axiom as circuits do. So in our generalization, the generalization of matroid that's useful for us, the only difference is that we no longer have a finite ground set. We have an infinite ground set, which is indexed by sort of monomials inside of C double bracket T1 times C double bracket TR. And the idea is that the tropical semiring is exactly generated by minimal support elements in, so it's generated by the supports of the minimal support elements in the local algebra of the singularity. And according to, and it's actually generated by minimal cycles, or in other words, circuits, where we just allow our ground set to be infinite as opposed to finite. So I think I will end there.
Comments? Questions?
So you probably said, but maybe I didn't pay attention, so your curves span the space? Or do you allow them to live in smaller dimensional linear spaces?
Oh, I'm always going to assume that they're linearly non-degenerate. Yeah, I should have said that. Yeah.
Your maps are birational onto their image or its image?
Yes.
Yes, you also assume that.
Yeah. I also
okay, so third question is, can you do any enumerative geometry on these modular spaces?
So, I mean, at present, no. But I think it would be natural to try to do that in the case of these hyperelliptic semigroups, for example. Because there we have, somehow the parameter space looks relatively well behaved, and we understand most of its dimension theory. But I don't know at this stage.
Thank you.
Okay, thank you. So Ethan, you mentioned an equality in the conjecture. Does inequality hold?
Equality for?
Inequality. The conjecture is an equality, right? The dimension or the codimension is equal to something. Do you know less or equal or greater or equal?
Yeah, I mean, I think the statement is that I think we always know that. I think that we always know that there are at least that many conditions. We just don't know that they're exhaustive.
Okay, right. And most of what you're telling us is the case where you have just one singularity, right, in the curve.
So it'd be much more complicated if you.
Right.
Yeah,
it's not just G nodes. I mean, it's much more complicated.
Something basic thing that has always troubled me. You know that ramification is additive if you vary the choice of point, but you don't know anything about conditions beyond ramification. So I think probably there are many ways in which the formalism that we're working with could be improved, and maybe with a better formal perspective we could be able to say something. But I don't know.
Okay.
Yeah, I mean, establishing some kind of dimensional transversality statement would be really nice, but I have no idea how to do it.
Okay.
So in this last case you consider lines through a point.
Yeah.
Have you tried to look at the combinatorial data given by the associated hyperplane
arrangement?
Yeah.
I mean, that's occurred to me, but I don't know. I mean, it's a natural thing to think about, but it's certainly a fair comment. I don't know.
If there are no more questions and comments, let's thank Ethan again.